Hi and hello everyone. What we will see in this lecture is about the transient solution or time dependent solution to the queuing system or queuing model. Okay. As you know, like we have considered so far only the steady state solution or equilibrium solution or what is the long run behavior, right. So, it does not taking care of what might happen or what might be happening with the system in the beginning when the system is basically starting. Okay. If we want to know about that part, then what we require is the transient solution or time dependent solutions, right. And this one only, like as this time tends to infinity, only what we are going to get is the limiting distribution or stationary distribution or steady state distribution. That is what we have been concerned with. Okay. So, that is the reason being that that is easy to handle, and for most of the models, right, that you might have in mind, that might be a sufficient one to get a first hand understanding of what is the system is all about, right. But one needs to remember that the steady state results, right, the drawbacks is what then probably like we are listing down here some of them, but may not be all. So, these steady state results exist only under severe restrictions, unlike the transient solutions, right. And the condition that we impose for the stability of the system may not be true, or it may be a little severe on the system. Okay. In many potential applications, the steady state measures of the system performance do not make sense for systems that never approach equilibrium. Suppose if you are looking at in a finite amount of time, and you will start and you will finish in that finite amount of time, then the system never reach an equilibrium state. So, the analysis do not make much sense in that cases as well. Okay. Again, the finite time operation is what is main thing that you have here, and time dependent analysis helps us to understand the behavior of the system when the parameters involved are perturbed, like what could be the immediate impact of the perturbation in the parameters, right. It might keep changing, right. So, that is what is happening, that you can immediately see, rather than waiting for again for the system to become an equilibrium state and then looking at its involvements. Okay. Again, another reason could be like two models may have the same steady state results, but the transient behavior may be different, right. We have already seen with respect to the discouraged arrivals queue and the infinity model, like this is what is happening. And the transient analysis contributes to the cost and benefits of operating a system in a more accurate way than the equilibrium analysis, and it is also very useful to obtain optimal solutions which lead to a better control of the system, right. I mean, this for I am giving one reference, but there have been a lot of work after this as well on why the transient analysis is needed to be studied in a queuing model as opposed to only the steady state analysis. Of course, steady state analysis you will do in the first level, right, but if you want a finer understanding, then obviously you need to know the transient analysis, right. Even in case where the steady state does not exist, say for example, in an MM1 queue, we know that for rho greater than or equal to 1, we do not have a equilibrium distribution. But even in such cases, right, if we want to know how it is behaving, right, it does not have an equilibrium, so it does not reach an equilibrium, right. But in a finite amount of time, it is not going to explode, right. So, things are going. So, how it is behaving, whether it is even within that, how it is its behavior, if you want to know, the only recourse that you have in your hand is the transient analysis and the time dependent analysis, right. Since the quantities, right, the equilibrium, the limiting probabilities are 0 in that particular case, right. So, but how quickly it is reaching to 0, right. and what is the rate at which it is reaching, right. If you want to, you can look at little bit more closely, about the instability of the system. If you want to study, you can look at more closely how quickly it is going into that particular state, right. So that is what would be the helpful nature. So this does not require that any condition of that nature in that cases, right. So in many practical applications, what you require is an analysis that deals with the system's behavior for a finite amount of time, and initial conditions also will have an impact on that. So if you want to study, then you need the steady state analysis. Then why we are not doing it, or what the difficulty in doing it, right. But if you look at the analytical solutions, or the analysis is much more complex, as we will show now with 3 examples, right. We will take it up 3 examples to exhibit the complexity in the solutions as opposed to their corresponding equilibrium behavior, right. What could be the the level of complexity that one needs to handle, and whether that much effort is worth putting in, it depends on the situation. If it requires, then obviously you need to put, but then one needs to be prepared for the more complex analysis of the queuing model, as opposed to a much easier way of handling in the equilibrium scenario case, right. So let us get started. So if you go beyond Poisson exponential assumption, this becomes even more complex, but we will restrict. But even out of these models that we have considered, we are going to give an overview. We are not going to go in very detail of every details of this solution. We will just give an overview to show you how complex the solution is, how critical the analysis would become if you want to really get into that. Then you need a lot of much more machineries than what we have at hand right now. But still, you want to give an overview so that you get a feel of what is this transient analysis or transient behavior would mean, and how one can go about doing it. Okay. So let us get started with this simple model of MM11, right. Very simple model. There is one server and there is no queuing happen. So this is a last system sort of things, right. MM11 model, very simple. So there is no waiting in this situation. So only there is one parameter lambda naught. It's a 2 state, 0 and 1 are the 2 states, and 0 to 1 it goes at the rate of lambda, and 1 to 0 it goes at the rate of mu. So this is what is the simple 2 state irreducible Markov chain scenario, right. So the rates are lambda and mu. Then if you write the corresponding equations, the forward Kolmogorov equation, that will be satisfied by the system state probabilities or the system size probabilities, which is Pn of t, then they will be given in this manner, and you also know P naught plus P1 for all t must sum to 1. Now we can also assume the initial probability distribution to be that the probability of the system starting in 0 at time 0 is alpha naught, and starting in 1 at time 0 is alpha 1, such that alpha naught plus alpha 1 equal to 1. Okay, so this is the initial distribution. So what we have now is that this forward Kolmogorov equations, and this is the initial condition. So we need to solve this system of differential equations, right, subject to this initial condition. So it is a initial value problem in that sense. So this is what you need to look for it. So we need to solve the above problem to get the transient solution. What we want is this quantities P0 of t, P1 of t as for all t greater than or equal to 0 is what you want, and at 0 it is given as the initial condition. Then for t strictly greater than 0 is what we want an expression, a solution to that, right. So now how do you do, right? We know that P naught plus P1 is equal to 1. So I can substitute P naught as 1 minus P1 in this second equation, right. So I will get, instead of P naught t, I will get 1 minus P1 of t, I can substitute in this second equation, and then we will get this as the case, P1 dash plus lambda plus mu times P1 t into lambda is equal to lambda, right. So, this is a very simple linear or ordinary differential equation which can be solved to get this as the solution with C as some constant, right. So, P1t is lambda by lambda plus mu plus a constant times e to the power this quantity. Now, this C is to be determined using our initial condition that P1 at 0 is alpha 1. So, if I P1 at 0 at t is equal to 0, so this is equal to alpha 1. So, this is equal to C, right. So, this is what you will get. So, C is equal to this alpha 1 minus this quantity is what you will get from the initial condition. Now, if you substitute this C here, right, if you substitute this C here, then what you would get is basically this expression as P1 of t, and P0 of t is 1 minus P1 of t. So, that will give you this expression. So, this is true for all t greater than or equal to 0. So, this is the solution. I mean, do not find too complex here because there is only a system of two equations and sum is 1. So, effectively boils down to a single equation, and once you solve this for P1 and t, which is a very simple linear ODE, you will get this solution and hence this. Okay. Now, this is what we call as the transient solution or the time dependent solution, right. Now, this in the limiting case, if we want the limiting case or steady state or equilibrium solution, we can find that because we know that P0 P1, the corresponding equilibrium solution is obtained by taking limit as t tends to infinity of these quantities, right. Now, once when you do that, right, as t tends to infinity here, right, this terms goes to 0 and this term goes to lambda by lambda plus mu, and this is mu by mu plus mu, which is essentially rho by rho plus 1 for rho or r in this particular case is lambda by mu. So, this is rho by rho plus 1 and this is 1 by 1 plus rho is what we have as the equilibrium solution, which you would have obtained otherwise very easily. Here it is not that complex here, right, but you know what is that you are seeing here is this as the equilibrium solution and this as the corresponding transient solution. This in the limiting, if I take t tends to infinity, I will arrive at this particular quantity, right. That is what you are seeing it, right. Now, let us look at how this behaves for certain parameter values in from this graph. We are assuming lambda is equal to 0.2, mu is equal to 0.4 and alpha naught is 0.1 and so alpha 1 is 0.9. That is the distribution that we are assuming, and for this parameter values the equilibrium solution is P naught equal to 2 by 3, P1 equal to 1 by 3. So, we know in equilibrium this is what it is, right, but how quickly it reaches here can be observed by looking at these lines here, right, these lines here. So, this value, suppose if I draw a line something like this is what would depict the equilibrium behaviors quantity, right. So, this is the quantity which is approaching to 2/3 and this blue line is what is as t tends to infinity, time is in the x axis, as t tends to infinity this will approach the quantity 1/3 and this will approach the quantity 2/3, right. But where it started and how long it takes to come closer, and the closeness you can define, right, you can measure it how close you want, accordingly you can think, right. It is even 0.6 is close enough to me, then of course it will take this much time to reach here. Suppose if I want much closer 0.65, then probably up to this much time. So, you can measure. So, this will tell you like how quickly it reaches the equilibrium, provided if one equilibrium exists, right. In this particular case it is the case, so we do not need to worry about that. So, this is what is the case here. So, this is what basically gives you transient probabilities. Now, if I extend this to 2 server case, for example, like you can still solve, suppose what I mean is MM22 model, suppose if I take it, right, I will still have a finite BDP which is solvable, but now I will have 3 equations, little bit more complex, and then like I will have one more line which will be drawing somewhere here, right. This total probability is 1, so somewhere here it will go and it will come here. So, whether it in what way it is reaching, whether it is reaching like this or it is going in this way and coming and reaching this, you do not know anything. That depends on the model, that depends on the parameters, right. So, with all these things, so if this in what transient behavior gives you is what happens in this pitch, in this part of it. So, once it reaches equilibrium, then of course, it is what you are going to get here. But up to this, right, how this is behavior of each of these system sizes and how what is its impact on this initial distribution, everything has to be studied. If you have to study, then you have to look at this portion. Maybe time unit 6 or 7, right, but what is the time unit, right? That is important, right. So, you can figure out like this, like what would be the initial behavior, and accordingly you can get the different performance measures, right. The mean number in the system, say at this point of time, at this point of time, at this point of time. It will also be time dependent, right. The waiting time at this point of time, how it is impacting, right. Everything one can study in a time dependent fashion if you have the time dependent system state probabilities, which is given by the transient solution. This model is quite simple, and what you need to understand is what does this gives us extra apart from the equilibrium behavior, right. So, that is this critical part, like in the beginning when you start the system, many system it just operates for a day, and every day it is a new cause, it never reaches an equilibrium, right, or every hour, or depending upon the context in which you are putting it. So, it never reaches an equilibrium, it is always in a transient state, right. So, that is another thing that you are looking at it, right. So, to do that, then obviously like one has to look at this behavior only, because of the obvious reason from the context. So, that is what one needs to keep in mind if we are doing a transient analysis. Okay, if it requires to be done, then these are the additional insights that you will get when you are looking at such systems. Okay. So, this is the first model that we have considered. Now, the second model that we considered is the ample server model, like the cell serves or MM infinity, right. So, in this case what we have here, assume for simplicity again, if it is slightly more complex, then of course I need to assume a initial probability distribution, but I am assuming a very simple form of the initial distribution, which is basically the system size is 0 at time 0, right. That is P00 is 1 and Pn0 is 0 for all n. Suppose if I assume that in the system starts with some I customer, then this initial will be according to that, or it starts with a probability distribution really, right, with one customer with this probability, two customer with this probability, then of course I will have much more complex situation. To make my life easier, like I will take this one easy. So, in that case, since we know that lambda n is lambda, mu n is n mu here, the forward Kolmogorov equations for P and T can be written in this. So, this is what now is the main equation that you have, which we have to solve with respect to this initial condition, right. Now, let us define this quantity as the probability generating function of these probabilities. Now, it is Z and T, right, is what is the probability generating function of these probabilities. Now, how we can obtain? For example, this second equation you can multiply by Z to the power n and sum over n and add this equation also, then you will arrive at this expression. Just for explicit, little bit more explicit, and I have written down here, which is basically the left side is basically dou the partial derivative of p with respect to t, and on the right side you will have a partial derivative with respect to z, right. That is what you have in these two terms, and these two terms will give you this. This is what is each of these terms will give you this. Ultimately, you are ending up with this partial differential equation, right. Now, this is the partial differential equation which is satisfied by the PGF of this. Now, you can solve this, right. So, that we are not getting into that business, but you can solve this. There is a standard procedure to solve. This is a very simple PDE, by the way, it is not very complex. So, you can solve this once you solve with this initial condition, right, what you will end up with this expression for the probability generating function of P and T, right. P001 which is equal to Pz0 is equal to 1. Now, if you have a distribution, then or if it is ith customer, then Pz0 would be like z to the power I or something like that, you will get it. If you really have a distribution, then you will have much more complex situation that will complicate this expression, that is all. Okay. Since you just want to exhibit the the overview or the context, so we will not worry too much on that. So, this is what ultimately you are arriving at as the probability generating function of this P and T. But now, by looking at this, like we know that this is the probability generating function of a Poisson random variable with parameter this, right. So, this if I take it as some parameter of this Poisson distribution, then I know that it is in the form of some say e to the power some delta times z minus 1, which is the delta is the parameter of the Poisson distribution. So, this PGF is the PGF of a Poisson distribution, and hence P and T then will be given by the Poisson distribution, which is what this quantity is all about, right. Or express this as a power series in terms of z and take the coefficient of z to the power n, you will arrive at this expression for P and T. So, here P and T, which is the transient solution or the time dependent solution of the infinity system with the initial condition with the 0, that is what you are getting it here, right. Otherwise, if initial condition changes, this expression also will have some impact on that, right. So, this is what you have it here. Now, this one, if you let t tends to infinity, we will arrive at this expression, which is what earlier we have obtained it, right. So, here also, apart from with our initial assumption, because of this initial assumption, this problem is not that much complex even in this case. It ends up with a one partial differential equation, and if you solve that partial differential equation, then you will get the solution for this generating function from which you can obtain Pn of t, and this is what is the transient solution. So, you can look at now again how quickly it goes. Now, you go back to the discouraged variables Q, which also has the same probability distribution in equilibrium or in steady state, but for infinity this is the transient solution. Now, for the same model that we have said about the discouraged variables Q, which is lambda n equal to lambda by n plus 1 and mu n equal to mu, right, this which will also have the same equilibrium distribution. If you look at its transient solution, that will be much more complex expressions you will get that, okay. But that is different from this one. One can compute and for fixed values of n and t, and then you can show that this is different, but both of them tends to the same limit this as t tends to infinity. So, if you want to look at now like the transient behavior of this, really they are different, one can exhibit. Okay. So, this is the infinity model. This is the second model that we are giving an overview of the transient behavior, right. We see that this model is also not too difficult for its analysis of the transient behavior. Okay. Fine. Now, let us take up what we thought is the simpler model to start the queuing analysis, which is the MM1 model, right. We started with our queuing analysis with this MM1 model. Now, let us look at the transient behavior of this MM1 model. Okay. This transient solution of this MM1 is quite complicated. So, we present only an outline of it, and there are many different approaches which gives you different forms of answers, transient solution for this particular model. Of course, all of them would lead to the same equilibrium distribution, but the transient behavior can be expressed in many different ways depending upon which approach that you are picking. There are plenty of approaches to obtain the transient solution, and hence different kinds of expressions, but if you compute all of them will land at the same value, that is a different matter, right. Obviously, it has to be. Now, we will assume that the initial system size at time 0 is some I. So, we are not starting with 0. For simplicity, if one wants, you can even assume that you are starting with an empty system, things will become slightly easier, but otherwise not much. So, P, that means that what? Pi 0 for some fixed I that we have assumed is equal to 1, and Pn is equal to Pn of 0 is equal to 0 for all n not equal to I. Now, in this particular case, lambda n equal to lambda, mu n equal to mu. So, the forward Kolmogorov equation are really now the differential difference equations. So, in the steady state analysis, you have only difference equations. The differential component was not existing, but here you really have a differential difference equations governing the system state probabilities to be given by these two equations, right. Now, we need to solve this equation with respect to this initial condition. That is all we have to do. Looks similar to the earlier, but let us see how we can do. We will give an outline of an approach which is due to Bailey, given 1950s, to solve this equation using a combination of generating functions, partial differential equations and Laplace transform. For which what we need, we define, as in the infinity case, we define the probability generating function of this P and T's to be Pz of t, which is given by this expression, and at least you know that this will be convergent, this series will be convergent within this unit circle, right. And its Laplace transform, meaning the Laplace transform of the generating function is this, which is equal to this. Or equivalently, you can also talk about Laplace transform of these probabilities and their generating function. Whichever way you arrive at, you will arrive at this, right. So, this is what is the Laplace transform of this probability generating function. These are the two quantities that we have in hand. Now, like this infinity case, you can multiply the first equation by the z to the power 0 and this equation by z to the power n, and sum you will obtain a partial differential equation, right. Now, you take the Laplace transform of that equation, right, and solve it. If you solve, then you will arrive at this kind of expression for the Laplace transform of the PGF of the system state probabilities, right, time dependent probabilities, right. So, where z to the power I you would arrive at because of this condition, because if you put this inside this at time 0, then what you will get P z 0 would be z to the power I. So, that is what is coming here, and z times of this and so on, and you also have another quantity which is P 0 bar of s, which is basically the Laplace transform of P 0 of t, right. Now, we need to determine, this is a typical approach, which the approach is also applicable later on. You will see immediately when we are looking at the general Markovian model, even in steady state analysis of some complex Markovian type model itself, this similar approach would be valid, right. So, you will have the generating functions or its Laplace transform, which will have one constant. Now, we need to determine this quantity, right. How do we determine that? To determine this P 0 bar of s, we use this fact. What is this fact? The Laplace transform, this one converges in this region, right, that we know. So, wherever the denominator, so if that is so, which means that in the unit circle, right, and real part of s is greater than 0, for which this is convergent. So, if there is a 0 for this polynomial, then that must also be 0 for the numerator, otherwise this convergence cannot happen within that region, right. So, wherever the denominator of this expression, the right hand side, has zeros in that region, so must the numerator. So, this is the fact, this has to be used even in equilibrium analysis when we move to the next complex models, right. So, when we are trying to determine any constants or any other unknown quantities in the expression for the generating function or its transforms in this particular case. Now, if I look at this denominator, it is a quadratic in Z, and if I look at this one, right, if I look at this expression, it has two zeros, right, it has two zeros, Z1, Z2, which is given by this expression, as you know, like with one plus and minus, right. It is the usual one that you have here, right, is what these are the two zeros, where the square root is taken so that its real part is positive. Now, you can observe that in absolute values, like Z1 is smaller than Z2, right. Obviously, you have minus here, you are subtracting a quantity. So, this must be smaller than this, and their sum is this and product is this, which is usual thing when you have a polynomial or a quadratic equation. What is the product of the roots and the sum of the roots, which can be given in terms of this is what you have it here. So, these are certain observations that you make with respect to this here. Okay. Now, this following theorem, Roche's theorem, is from complex analysis, and it has wide use in queuing analysis, even in equilibrium analysis. Okay. So, we are going to use it when we take up next the more complex Markovian models equilibrium analysis. Again, this theorem would be applicable. Okay. So, this theorem is important in that context. So, it is better that not just from the transient analysis of this model, but even otherwise, even in equilibrium analysis, we will refer to this theorem from the complex analysis and we will use this, right. So, you better be aware about this theorem and how we are using it actually. So, what is this theorem says is the following: if f of z and g of z are functions which are analytic inside and on a closed contour C, and if mod g is less than mod f on C. See here, the functions are analytic inside and on the closed contour, and what we require, this mod of g is less than mod f on the boundary on C, right, and the closed contour. Then what one can infer is that f of z and f of z plus g of z have the same number of zeros inside C. So, you have a closed contour, right, and you have two functions f and g which are both analytic inside and on means the boundary of this contour. Okay. And what you are observing is g is in absolute value is smaller than mod f. See, they are all complex, right, complex numbers. So, you have this complex function that you have here. So, this mod g is less than mod f on the boundary, then inside the contour C, inside C, you have f, which is the dominant one, and f plus g, the dominant one and plus the dominated one, f plus g. So, the dominant one and the dominated plus the dominant one both have the same number of zeros inside the contour C. That is what it says. Okay. So, let us see how we are using it here. So, we are taking the contour to be this mod z equal to 1 and real part of s greater than 0, because we already said that within that things are nicer, right. So, in this we observe that my f of z, right, f of z is basically this quantity which is there as this expression, and this quantity you will take it as g. That is what you are going to do. So, f of z, right, is basically this quantity is equal to this quantity, because mod z equal to 1, and this real part of s is greater than 0. So, this means this will be strictly greater than lambda plus mu, right, and so this is strictly greater than or equal to mu plus lambda z square, and this is what you have it as g of z. So, g of z is less than f of z, then f and f plus g must have the same number of zeros inside this region, that is mod z less than 1. Okay. Now, from Roche's theorem, right, using that theorem, then f plus g, which is exactly this expression, has only one 0 in the unit circle, because your f has 1 0 in the unit circle, right. So, this f plus g also has 1 0 in the unit circle. Now, out of these two zeros z1, z2, because z1 is less than z2, that must be z1, and so Z1 must also be a 0 for this expression. That means it must vanish, the numerator must vanish at Z equal to Z1, and if you do that, then this is what you will get it as P naught bar of S, right, P naught bar of S. Now, if you substitute this P naught bar S here, then the right hand side is fully determined. Now, like you can express as an infinite series, and noting that this is the case, we can obtain the expression for the infinite series expression for this Laplace transform of genetic function to be this. This is with little work, it is not too complex here. Once you plug it there and then express it, then you will get it into this form. So, this is what you get as an expression, right. Now, what we need, so basically what we had this quantity obtained, which is the Laplace transform of Pzt, and Pzt has in its coefficient Pn of t. So, if I look at this, if I look at its expression in the sum, I can plug it this quantity, this whole expressions here, I can interchange this integration and sum, the inside one will be the Laplace transform. So, if I look at in this expression, the z to the power n's coefficient, it will be the Laplace transform of this quantity, right. So, that you can first obtain, right. So, this p bar ns is the coefficient of z to the power n in this. Now, extract it and then invert that quantity to get Pn of t. Now, how do we do? We have to utilize now some properties of the transform of Bessel functions of first kind. This is a integral function or the special function in mathematics, right. You may or may not know, does not matter, we will not worry too much on that. So, it is using the Bessel function of the first kind, which is denoted by In of y. Using its transform and some of its properties, you can do, it will be some 2-page workout that if you do, finally you will arrive at this Pn of t, which is given by this expression, where this In of y is given by this infinite series is the modified Bessel function of the first kind, is modified Bessel function of the first kind, sorry, not just the Bessel function, it is a modified Bessel function, here also you have to use this. So, ultimately what you see is this expression, right. What is this transient solution of this Pn of t? It is in terms of not just the modified Bessel function, but it is also a series of modified Bessel function, which itself is a series, right. You have lot of complexity built in here in terms of this you are expressing, right. So, this is what is the transient solution that finally you are obtaining it, okay. But if you use again using the properties of the Bessel functions with a little work, one can show that Pn of t, which is this quantity, as t tends to infinity, tends to this quantity 1 minus rho to the power n. Effectively these terms would vanish in a way, right, and this term inside this everything would give you rise to 1. So, leaving out with only this kind of quantity, that is what you are saying whenever rho is less than 1. Okay. When rho is greater than or equal to 1, this will be tending to 0 as expected, right, which agrees with our earlier result, which is known to us when we analyze simply the equilibrium analysis. Now, you see this is the equilibrium solution and this is the transient solution. You can see the complexity of this here, that the plus here is that this is applicable for any rho, right, you can compute it for any rho. And whereas this one is we can talk only with respect to rho less than 1, right. So, that is what you have here, right. So, this is one outline, we will not worry about too much how we are obtaining this and everything, is just to give you an outline of this. So, here what you will take with you forward is this Roche's theorem and how we have applied this Roche's theorem in this particular situation, which we are going to use it even later, even in equilibrium analysis. So, this result is what then you have to remember going forward, but that is the result that we are using it to sort of explain the nature of transient solution. But the advantage, disadvantage both are there, right. Rho greater than or equal to 1, there is nothing like equilibrium analysis that you can do and then you can get something. But here I can understand, I can see how quickly it tends to 0, right, by looking at this Pn of t for each n and so on. So that I can get an idea about how things go or how quickly the equilibrium is reached here. So what do we have? Now 3 models that we have seen with different complexities. Now the more complex the solutions will become if the model is going beyond even Poisson exponential assumptions. Within this framework itself, if the rates are complex, right, things are become very complicated, and there are many different models for which even there is not an solution, transient solution is not yet been found, because it is so complex in that case, right. So it is extremely difficult to obtain, but then what is the alternative? That remember, this is ultimately, after all, is a system of differential equation based upon an initial condition that you are trying to solve. So any numerical procedures, anything available to do that, one can utilize it, which can be successfully employed to at least get numerically solvable ones, right. So often what happens, the special structures, like in the case of BDP, you have this Q matrix, right. So this Q matrix is a tridiagonal structure, right. So this special structures always have some specialized procedures which can be executed in a more efficient way to get the solution in a much lesser time. And there could be approaches which might rely on such structure, say for example a continued fraction approach, or even any other combinatorial approach, or many things that one can talk about with respect to numerical procedure itself, with respect to even birth death queues. Forget about more complex queues. But the more complex queues that you have, like this numerical techniques will become bit more complex, but still it is doable. So whenever you are not able to do this, you can always appeal to the numerical techniques to get the solutions. Okay. So that's about the transient solution of this queue. Probably you would have got an idea about how complex the transient solutions can become, even for simplest of the simple queuing model, which is MM1, right. And but if there is a need, if you have to do, you have to do it. If you are not able to do analytically, appeal to numerical techniques. And there are plenty of numerical methods to solve Markov chains, so that can readily be used here, right. So we are not concerned about that part, or one can go for approximate solutions, things like that, but that is beyond the level that we are talking about here. Okay. Now once we have done this transient analysis, like this can be used to some kind of analysis which is also required to be done for some kind of models, that if you have to look at it, then how one can adapt this analysis approach to do this, and that is called the busy period analysis. So this is also relevant for many queuing models you want to do. What is that busy period? A busy period is basically the time when a customer arrives at an idle channel when the system is empty, and ends when the channel next time, for the first time it becomes idle again, meaning system was idle, now a customer arrives. So your count, the time count starts there. Now this customer is getting served first. So we are looking at it in the context of MM1. So this arriving customer service starts immediately because he is arriving to an empty system. Now when next time the system becomes idle again, meaning what could have happened is that during the service time of this first customer, there might be customers arriving, right. Now if you take into all their services, and during their service time another customers might come, and so on. So it goes on, and the server is kept busy serving customers, and at some point of time again the server will become idle, right. In a steady state situation that will happen, right. It will become idle, then only the steady state, because any state is all recurrent, right. It has to be past recurrent, means it will come back. It will come back in a finite amount of time. So there is always a time at which it will become empty again, or it will become idle again, right. So from this point till that point, that is what is called as the busy period. Meaning is also very clear that it is a busy period for the server. Server is kept busy during that period. Okay. So this is the random variable which we call TBP, and this is basically the first passage time from state 1 to 0, right. Because from the time the state is 1 till it reaches for the first time to state 0. So, the first passage time from state 1 to 0 is what is the busy period. Now, a busy cycle is the sum of a busy period and an adjacent idle period. The idle period could be the previous one or the succeeding one, preceding one or succeeding one, whichever way it is. Anyway, both of them are same, right. So, it is the sum of these two is what you call it as a busy cycle, which you can relate as a time between two successive departures, which is leaving an empty system, or two successive arrivals to an empty system, right. This is what will be a busy cycle. Now, in the MM1 context, the idle period will follow an exponential with parameter lambda, because this is the residual inter-arrival time in a Poisson process arrival cases, right, which is again because the memoryless property you have this as exponential lambda. But if you know the distribution of the busy period, then the distribution of the busy cycle is basically sum of these two random variables, right, idle and busy periods. So, the CDF of the busy period can be found by considering the original MM1 equations and by observing this to make adjustment for this kind of behavior, the first passage time from state 1 to 0. So, how you can make that, you take the same set of equation, you will make state 0 as an observing state, right. So, for which what you have to do, you have to take lambda naught equal to 0 and you have to start at state 1. So, the initial state is 0, right, initial state is 1. If the initial state is 1 and if you make 0 as an observing state, now if you look at the time until you will reach that is the duration, right. Then this P0 of t, it is basically that starting from state 1 reaching to state 0 by time t. So, is the CDF of the busy period and P0 dash will be its PDF, right. Now, in the original set of equation if you put lambda naught equal to 0, then the equation that you will get is this equation, right. It is slightly, I mean, with the lambda naught equal to 0 is what then you are getting this equation, right. So, P0 dash will be simply mu P1 because lambda naught is 0, the first equation. In the second equation also like lambda naught equal to 0. So, the P naught term will not be there. So, P1 dash will be P in terms of P1 and P2. So, this one. Now, again you can use the same approach ultimately, right, carrying out a similar analysis like what you did for the transient analysis of MM1, you will arrive at this P bar is at 0 as this, because now the initial state is specified clearly, like you do not have to assume anything else, you cannot assume anything else, right. So, then you will end up with this expression where Z1 Z2 like as in the case of MM1 transient analysis. But what we want this quantity, we do not want anything else, right. We have specifically this quantity which is if I express this as a power series, the constant term is what then will give me the P bar S, right. I can simply extract the constant term alone to my requirement and you can see that would be equal to this, right. Now, again you have to invert this to get P0 of t. If you do that and then or you can take its derivative, which is much easier, you will arrive at this expression and this is the probability density function of the busy period. Now, again you can obtain using the limit theorem for the transforms, the expectation of this quantity is basically the negative of the this quantity, right, is what then you would find, and that will be equal to 1 by mu minus lambda as you will obtain, which is the expected duration of the busy period, right. And expected duration of the idle period because this is exponential lambda, it is 1 by lambda. So, the sum of these two will give you the expected duration of the busy cycle that you have. Now, this is the PDF of the busy period. So, if I want to know the distribution of the time, right, the busy period time, then what you would arrive at such expression, again this involves the modified Bessel function of first kind. But this expression can also be obtained in an alternative way, which is much easier, which is applicable to more general as well, by using the simple steady state ratio argument, right. What is this 1 minus P naught? 1 minus P naught to P naught. This is the proportion of time or fraction of time the system is non-empty and this is the system is empty. So, this must be equal to the proportion of or the expected duration of the busy period to expected duration of the idle period, right. So, this ratio must be equal, This is the steady state argument, which basically comes from a renewal theory argument, but does not matter, you can easily understand it in this way. But we know expectation of T ideal is 1 by lambda, and we also know P naught is equal to 1 minus lambda by mu in case of single server systems. So, if I plug it that, I can compute expected duration of the BC period to be 1 by mu minus lambda as we obtained it earlier, and hence expected duration of the BC cycle is sum of 1 by lambda plus this quantity. The advantage and the beauty of this result is that this result, which is expectation of BC period duration or expected BC cycle duration, holds true for any MG1 type queues. As long as the arrivals are Poisson process, for any service time distribution, this holds, because in this derivation, like the service time distribution did not play a role here, in this case at least when you are. So, this is true for any MG1 type queues. So, this BC period is basically another performance measure with respect to the server, right. With respect to the server, if you want another performance measure, then this is the ideal period. BC period is what you can talk about, right. We said that there are different angles to the system when you look at the performance measure, but this BC period analysis, if you want in detail about its distribution or the duration of the BC period, or you want to know, say for example, how many customers are being served during a BC period and so on, then you need a much more detailed analysis which will have similar complexity as the transient analysis case, but with slightly less complexity, because you would need only like this kind of one term depending upon this, right. But this average case analysis one can get very easily using this kind of argument, and anyway we already said that this result is to hold true for any MG1 type queues. So, like this, like then you can have it for multi-server case, you can easily extend this idea, right. So, you can talk about variations of this BC period, but we will not be concerned more about this. But if you are interested, but of course one can do this kind of analysis, but this will be a little bit complex. That is what you need to keep in mind, right. So, with this then we end our discussion on the complete birth-width queuing systems. We have seen, even given overview of this transient analysis in this lecture. The take home from here is mainly the Rauch's theorem, and it is how we can apply here, and the complexity of the transient solution if you want to obtain. Now, alternative could be that numerical procedures can be applied, and this helps us to get the BC period analysis as well, and this result is true for MG1 type. That is what we will take. Okay, we will see later. Thank you. Bye.